Hi class, welcome to Online EdVantage. I'm Dr. Scott Adamson, and today we're going to look at line integrals. But before we do, please subscribe to our channel. So, you've seen some previous work with line integrals, but this example is going to be a case where we're going to have to parameterize a curve first. But before we even start with that, I want you to get a sense for what a line integral measures. So let's go look at a graph.
So the problem we're going to solve by calculating a line integral involves the vector field f of xy is equal to yi minus xj. So what you're looking at now is a graph of that vector field. The pink arrows are showing that. You can tell that it's the correct vector field because when x is 0, then y is 1, 2, 3, 4, for example. The vector field only is pointing in the to the right, the positive x direction. And if you look down here, when y is 0, then only and x is positive, we see vector fields pointing just straight vertically. So the question is this. Metaphorically speaking, if this vector field was to represent, say, the flow of water in a river or some body of water, and metaphorically speaking, if we were traveling through that body of water along this parabolic curve that you see here in red, the question would be is this: does the current in the river aid or hinder our traveling from, and the problem was from x equals 1 to x equals 2. So as we travel metaphorically along this curve, does the current in the river help us or hinder us? So notice here, we're traveling in a direction that is mostly in line with the current in the river. And that alignment gets less and less, say, into here. But then as x gets closer to 2, we're more in line once again, although the magnitude of the vectors is relatively small, so the help we're obtaining from the current in the river is relatively small. But overall, as x increases from 1 to 2, our path in the river, metaphorically speaking, is mostly in line with the current in the river. So we would expect the line integral in this context to be positive. Let's go compute the line integral and see if we're right.
So we've seen with the graph that the line integral through this vector field along this curve should come out to be positive. Remember, line integrals are accumulating or summing up lots and lots and lots of dot products. And dot products are positive when the two vectors are, relatively speaking, in line with one another. And so we saw on the graph that the path we were taking and the vector field were relatively in line. So we would expect a positive line integral. Well, let's compute it and see. Now the process for computing a line integral, there's several pieces to it, but the first piece is we need to parameterize the curve. So the curve that we're on is this parabola, y equals negative x squared plus 4, but just between, x is between 1 and 2. So to parameterize this curve, most simply anyway, let's let x equal t. Now, once we make that decision, we don't just get to willy-nilly do whatever we want for y, because y is defined by negative x squared plus 4, and if we do let x equal t, then y must be negative x, so negative t squared plus 4. So here is the parameterized version of that parabola. Now, we can express that as a vector-valued function. We'll use r. Conventionally, the letter r is used for vector-valued functions, these parameterized curves. And so the x component is t, so ti. The y component is negative t squared plus 4j. So there's our vector-valued function r of t. Now, metaphorically speaking again, we're on this curve in that vector field, and we want to make sure that we only consider points in this vector field yi minus xj that are also on that curve. So as we go to compute the line integral, the second step would be to find f evaluated at r of t. Now, to do that, the function, the vector value function, the vector field is yi. The y component that we are focused on in this particular case is negative t squared plus 4. So as we compose these two together, yi is going to become negative t squared plus 4i minus xj. And the x component on the curve that we're on is just t. So minus tj. So now, by composing these two together, we're going to be able to examine the dot products between the vector field f, but only at places in the vector field that are also on the parameterized curve. Now remember, in step 3, we need dr. And so, we need the derivative of r. So we just differentiate each of the two components of that vector valued function. The derivative with respect to t, by the way, it's really the derivative with respect to t. But as you've seen, we're going to multiply that differential dt to the right side. So let's just do that in this step. So the derivative of t is just 1. So we'll have 1i. The derivative of negative t squared plus 4 is just negative 2t, so we'll have negative 2tj. And then remember that differential dt gets multiplied to the other side. So now, we've got f at r of t, we've got dr, and we finally can get to the dot product between them. So we're going to take f, and we're going to dot it with dr. Now remember, in this notation, we only say f because we get a little simplified in our writing here. We'll just say f, but we know in our heads that this f is referring to f at r of t, not just the general vector field f. So let's go ahead and dot them. Now remember, the dot product between two vectors is a scalar. So we're now going to transition from all of these vectors and vector fields and vector valued functions. We're now going to transition to a scalar result, the dot product between f and dr. So we take the x component here, multiply it by the x component here. So negative t squared plus 4 gets multiplied by 1, which is just negative t squared plus 4. Plus, we take the j component or the y component here times the j component or the y component here. So it's negative t and negative 2t. So it's plus 2t squared. And then don't forget our differential dt. Let's just do one more quick step of simplifying here. Negative t squared plus 2t squared is going to be positive t squared plus 4. So there's our dot product. Now we can accumulate all the dot products between 1 and 2 according to our integral. So we've got the dot product. So now the line integral computation really comes down to this. We're going to integrate f dot dr. That is, we're going to sum up all of those dot products between the vector field and that parameterized curve we're on the interval from a to b. And that accumulation of dot products, as we predict, should be positive something. Let's see. Now, the interval from a to b. Remember, in the unparameterized curve, x was only between 1 and 2. We parameterized by letting x equals t, and so now t is also going to be between just 1 and 2. So our integral is going to look like this. We're going to integrate from 1 to 2. F dot dr. And if we look back at our step 4, f dot dr turned out to be t squared plus 4 dt. Now we just have a nice single variable integral to deal with. Let's do it. The integral of t squared is 1/3 t cubed. And the integral of 4 is 4t. Fundamental theorem of calculus will evaluate that antiderivative between 1 and 2. Start by evaluating at 2. Let's see, 2 cubed is 8 A third times 8 would be 8/3. 4 times 2 is 8. So evaluating this antiderivative at 2, we'll get 8/3 plus 8 minus, fundamental theorem of calculus, we subtract the value of this antiderivative at 1. 1 cubed is 1 times a third is a third. 4 times 1 is 4. So all told here, we have 8/3 plus 8 minus 1/3 plus 4. Grab a calculator if you need to and compute all that. But all of this comes down to 19/3 or 6 1/3 if you like. Now we shouldn't be surprised that this integral came out to be positive, that this line integral, this accumulation of dot products was a positive, because we saw in the graph that the vector field and the parameterized curve were, relatively speaking, in line with each other with those acute angles between the vectors. So the fact that we have a positive here is not surprising. Now, continue on to the next video, and we're going to see how might we attack a line integral without parameterization. Come on back and see how that works.